To Maciej opowie nam trochę o Azurze Allegro Pay. Także już dodaję Tobie ekran i ja już się usuwam. Także dzięki Maciej.
All right, so in case you haven't been notified, this talk is going to be in English. In case you'd like to contact me directly, on the right-hand side, you can see what's my typical technology stack. This is either stuff that I'm working with on a daily basis or something that I'm very, very passionate about. So without further ado, first we're going to talk, so what is this Azure thing about? So Azure has been with us for a while now, and it all started in late 2008 when, during one of the conferences, Microsoft announced that it's working internally on something large, and that this something large was internally codenamed Project Red Dog. And in February 2010, Windows Azure was released. Initially, it was just a few data centers in a few regions. And the initial model of the service was very, very simple because it was called cloud services. So we used to code stuff, package it up, and ship it to the cloud. And whenever we were trying to scale it, we would have to provision a new virtual machine for each replica of a service that was being deployed. So this wasn't very performance effective. However, it was very cost effective, and I'm quite confident that people from accounting loved it. So this situation has transpired for about 4 years. And in mid-2014, the whole thing was rebranded to Microsoft Azure, and a new management model was introduced. That management model is called ARM. The abbreviation stands for Azure Resource Manager. And it also came with a brand new HTML5 portal. So if you remember, at this time, HTML5 was a new thing, and it was lead and hot. However, that portal was quite short-lived, because about a year and a half later, a new version of the portal was released, one that is with us up until today. Its internal code name was Ibiza, and this version of the portal was intended to stay with Azure for the long run. It's, you could say, very expandable internally. So whenever Microsoft is adding new services and new features, those get represented in the portal's user interface quite frequently and quite easily. So a few years have passed, and imagine yourself being in early 2020 when the COVID pandemic breaks out in Europe. And incidentally, Microsoft says that it's going to allow people to use Teams for free if they're pupils in schools. They're going to let people in kindergartens use it to teach children. And also, it's expecting that people working from home were use Teams more and more. And they've noted a 775% increase in Teams utilization. They said, okay, we can handle it, we can take it. And for the first month, there were some interesting situations. However, during this time, Microsoft has worked on increasing the infrastructure services behind Teams worldwide, and they've managed to handle it, and they continue to do so until today. So hats off. And a few months later, they've also announced that Poland is going to host a new Asia region, which is going to be codenamed Poland Central. I don't think there's been a precise announcement on the date. However, we could guesstimate that this region is going to be with us sometime next year, probably. Okay, so speaking of regions, so what exactly is a region? So from Azure's perspective, a region is a collection of data centers, at least one. So as you can see, in this particular scenario, we have two regions that one of them consists of a single data center, and the other region consists of 3 data centers. And those 3 data centers are connected to each other, and they form something which is called availability zones. This typically means that those availability zone-based data centers are adjacent to each other, and the distance between them does not exceed 10 miles typically. This is meant to keep the latency down to a minimum and constant between all the data centers, and that latency should be below 2 milliseconds. Microsoft also connects regions into regional pairs. Typically, the regional pairs are separated by about 300 miles with 20 millisecond latencies. This is done to ensure that services running in region A, provided you select a high enough tier, have the ability to replicate their data into the second region. So in case you have a region-wide disaster, your service will continue to function because the data will be replicated into the second region in the pair. So it is possible for multiple region pairs to exist in a certain part of the world, and in that particular case, we call it a geography. So a geography is a collection of regional pairs, and regional pairs is basically 2 regions, and each region can contain at least one data center. Okay, so we now should say something about the SLA options offered by Azure. So in case of a single virtual machine, assuming you're provisioning it with premium storage, in that case, Microsoft grants you 99.9% availability of that resource. We can increase it by putting the virtual machine into a construct called an availability set. In that case, we are talking about having multiple virtual machines, but those virtual machines are placed in totally separate physical racks within the data center that do not share anything physical. So for instance, if there's a power supply outage or cooling outage or anything else, only a single virtual machine in the availability set will be affected and the other will continue to function. A further increase of availability is offered by using availability zones. So this is the concept that we were discussing in the previous slide. And in this case, we're going into 99.99% availability. So an availability zone will protect you from an outage of a single data center within the region, but it will not protect you from an outage of an entire region. So this is why you should consider using multi-region disaster recovery. All right, so we've mentioned briefly the concept of the Azure Resource Manager, which was introduced in 2014. So as you can see, this is basically a certain hierarchical structure. So on top of it, we have management groups, which can aggregate other management groups. Later, this is a comfortable place to assign permissions for people which need to manage everything in a certain scope. Later on, we have subscriptions, which act as billing units, which aggregate billing costs from every resource that is deployed in their scope. Later on, we have resource groups, which act as logical containers, which make sense to deploy and delete together, also to control access to together. And at the very bottom, we have the actual resources. So those are virtual machines, networks, storage, automation, you name it. There's a lot of those services. So thanks to Azure Resource Manager, we have the capability to manage Azure in multiple ways. So that would be Azure Portal, a mobile application, ARM templates, Cloud Shell, PowerShell using the AZ module. There's also an RM module, but it's deprecated at this point. We also have Azure CLI. Microsoft is working on a new tooling, which is called Azure Bicep, which will be with us in the near future. There are also C#-based SDKs. And for those people who like to write their own tools or just to get their own hands dirty, there's a REST API available as well. So without further ado, so how do you deploy a typical Allegro Pay service? So our services basically own their infrastructure. So that means that whenever we are deploying a service, this also means that we have the capability to deploy the infrastructure that the service is an exclusive owner of. So typically, we have a multi-repo approach, and the entire code of the service and its infrastructure is contained within a single repository. We generate those services from a .NET New template, thanks to the tooling provided to us by the .NET SDK. So whenever we create a new service, it comes ready with an Azure pipeline and a deploy PS1 script and basic Kubernetes customizations out of the box. So this is the basic recipe for our service. Okay, so like I mentioned, Azure pipelines are available out of the box. So this means that each service comes with its own recipe to build it and to deploy it to subsequent environments. So in this particular case, we can see that an artifact is being built, and from my experience, I can tell that this is being done on the master branch. And having built the artifact successfully, the binaries will be used to create a container image, and that container image will be promoted to the UAT environment and finally the production environment. We also have other environments, but they're not used on this branch. And what you see here is a rolling update strategy. So what will happen is the Kubernetes cluster will schedule a new revision of a deployment, and once the pods are ready, following their update strategy, they will gradually replace the pods from the previous revision of the deployment. So this way we will achieve zero downtime. We also support canary deployments, and this also comes with some tricky mechanisms implemented in Azure DevOps pipelines. So we have the capability to deploy services to canary namespaces and direct a portion of the traffic to those services without affecting the primary deployment in the actual production. Okay, and last but not least, as you can probably tell, we have a lot of services, and having the capability to easily provision new services and deploy them in under an hour means that we need to put certain constraints on the way that our infrastructure is being deployed. So for that purpose, we are maintaining our own automation module, which wraps Azure ARM. And this is because we are functioning within a certain ecosystem of Allegro services, and there are quite strict expectations of us how we should integrate with our network, how should our resources be secured, how should we provision resources in a way that no public endpoints are exposed and the communication transpires only through private endpoints. So this is why this tooling was put in place first, and it's also meant to put a certain level of standardization in that department. Also, as you can see, our automation is built in a way that it's also buildable and, most importantly, testable as well, which is something that we enjoy quite a lot. Okay, so what can this thing do? Each deploy PS1 script contains a recipe for deploying the infrastructure owned exclusively by a given service. Also, the shared infrastructure makes use of this. And everything revolves about the Azure deployment settings object. So in this particular case, we need to feed it some information like what project do you belong to, what's the team that owns you, which subscription do you belong to, which environment do you belong to, what's your geographical location, because we have resources in multiple pieces of the world, and most importantly, what's the business module that you belong to. And based on that, we will render an ARM template with automatically generated names and tags, and we basically save our developers the trouble of interacting with raw ARM templates. Instead, they simply use strongly typed PowerShell objects. For those of you that didn't know, since PowerShell 5, PowerShell supports classes, and object-oriented programming, which is quite fun. We also use this to automatically configure peerings between our hub networks and our spoke networks. We also automatically configure private endpoints and automatically configure public endpoint firewalls. So the automation has proven itself over the last year, and it's quite useful to us. Okay, so having spoken a little about the architecture, we should ask ourselves, okay, so how are those clusters built? Okay, so like I mentioned before, there is a hub and spoke architecture. So that means that our on-premise data centers are connected to each Azure region using a redundant VPN connection. One is an express route, the other is a classic VPN site-to-site connection. And those connections end up in the regional hub VNet. And in the same region, other VNets exist. Typically, for each project, for each environment, we have a spoke VNet, and that includes Allegro Pay environments. So in our VNets, we typically have subnets dedicated to certain purposes, like hosting AKS node pools, like a system node pool or a main node pool, or a private endpoint subnet, because private endpoints also require that you provide them with some space to provision in, and anything else that we can come up with, really. So we have the capability to expand our virtual networks, and whenever we feel like adding something new, after some planning and consulting, we deploy new resources to those locations. Okay, I've mentioned private endpoints, and this is one of the most crucial functionalities of Azure that we are utilizing. Typically, when you provision an Azure service, it comes with two endpoints. One is the public endpoint, accessible through from the public internet, and typically it has an optional firewall with some exclusions, like this MS SQL database. In that case, the firewall is mandatory and with good reason. However, most of those resources also permit to provision something which is called a private endpoint. So what happens is a virtual network interface card is provisioned in the target subnet, and it tunnels directly to the private endpoint of that resource, bypassing the firewall, because the communication in this particular case is safe and trusted and happens only within our virtual networks. Okay, and how are our clusters modeled? So like I've mentioned before, we are using PowerShell, and since we have already pre-configured the deployment settings, we now need to configure the settings of the actual resource, in that case, an AKS cluster. So our objective was that one shouldn't interact with ARM too much unless they want a really heavy headache. And they should be able to easily declare what resources they'd like. So on one hand, we have the option to have something that is declarative. On the other hand, we get to benefit from the features of the language, which means that anything that you can put in the script is a go. All right, so what are we getting? So we are getting a private AKS cluster with dedicated subnets for dedicated node pools. So the system node pool hosts our workload, which is supporting the cluster itself, such as Prometheus, the service mesh, an autoscaler, which is Kata, and the ingress. And the main node pool typically hosts our services. And important thing to note is that the nodes themselves are placed in availability zones. So our virtual machines are separated by at least 10 miles. So in case there's a disaster in one of the data centers, that means that only a portion of our clusters will be hurt. So why have we implemented new AKS clusters? Before last Christmas, we've had an interesting incident. Shortly before Christmas Eve, during the peak of traffic, we found that we are incapable of scaling out our cluster. And this was because we've run out of IP addresses. The mask of the subnet at this time was /21, meaning that it could host up to 2043 IP addresses, and it turned out that our AKS was using 1998 addresses while only having 18 nodes. So that was interesting, and having analyzed the formula, we have determined that the pod limit was far too high for quite small virtual machines, which at the time were running only 2 cores and 7.5 gigs of RAM. And telling ourselves, yeah, we can fit 110 pods on such a node was probably an exaggeration, which left to us finding out that we were wasting IP addresses, and we have also lost the ability to upgrade the cluster in place, because whenever you do a cluster upgrade, the automation in Azure will provision a new virtual machine, and whenever it needs to do that, it reserves an IP address for that machine and the pod limit that you have defined. So for that reason, it turned out that we weren't capable of doing that anymore, and alarm bells went off. Okay, so how much addresses do we really need? So the amount of nodes times 1 plus the pod limit. So how does the new cluster compare to the old cluster? The old cluster at the apex of its glory was running 18 virtual machines with 2 cores each, so that means 36 CPUs and 135 gigabytes of RAM. The current cluster is configured to run at 33% capacity at the moment. We will most likely be increasing that before Christmas. So right now it has the capability to scale out to 30 quad-core virtual machines. So that means 120 CPUs with 450 gigs of RAM, but that's only 33% of what we can do today. And at the moment, we're operating at about half of that. So our true capacity is 90 virtual machines with 4 cores each. So that is 360 CPUs with 1350 gigs of RAM. So this is our full capacity, and this isn't our last word, because like I mentioned, we had the capability to expand our networks and add additional node pools in a repeatable and declarative way. So it's only a matter of time when we come up with something new. So how does autoscaling at Allegro Pay work? Like I've mentioned, we have an autoscaler which is called CADA. It's a CNCF project, which is really interesting because it basically exposes a custom metric server to the built-in horizontal pod autoscaler, and it introduces the concept of a scaler based on an external trigger source. So that can be something like a Prometheus metric, that can be a CPU utilization, or that can be an event, or something like a message in a service bus. So you could scale something based on such things. And CADA introduces 2 interesting CRDs, which are custom resource definitions. One is a scale deployment. So this is a classic Kubernetes deployment, which is managed by CADA for scalability. And the other is a scale job. So you can run a fire and forget jobs for each event that transpires in your messaging queue. So those are the capabilities that we're looking at very, very closely at the moment. We have introduced CADA as well as Linkerd about mid-May, and as you can see, it has helped us a lot, because during the traffic spikes, we used to have services which were frequently under too much load, and they were suffering from out-of-memory killed events. But having introduced that, we seem to have fixed the problem. An additional way that some of our infrastructure is being scaled is, for instance, using the Azure monitor. So in this case, we are telling the monitor to monitor the CPU usage of our service bus, and whenever there's a peak of CPU utilization, that service bus will scale vertically to handle more load. Another example is to have an autoscaling database. In that case, that's Cosmos DB. So this characteristic tells us that the database is idle most of the time. However, there are times when there are some peak activities, and we should have the capability for the database to adjust its resources to handle that. And this can be done very, very easily with Cosmos DB. You basically tell it that, hey, this is the amount of resource units that I typically consume, and the maximum that I want to go to is 10 times that. And you will get that for 1.5, 150% of the cost, but you're only charged for the highest amount that you've noticed during the billing hour. So the cost is quite negligible, and it's quite affordable and saves us the headache. Okay, so what else do we have here? Cost control. We are querying the Azure APIs to extract cost information about every resource that we possess. And this is something that we treat with almost, religious zeal. We need to be very, very mindful about what we provision, how we provision, and how we utilize it. And the reason is because sometimes we may have a situation wherein something spins out of control. In that case, an instance of Azure storage was subject to so many requests that it aggregated a cost of almost 2,000 euros in less than 2 days. So we need to be mindful, and this is also something that we're going to be working on so that we can become better at this. We also track the amount of money that our services cost while hosting them in the cluster. So this is important to us because we know that some pieces of our infrastructure are pricier than others. And we also track how much money do we waste due to services poor behavior or poor configuration or wasteful configuration. This is also something of interest because, well, money doesn't grow trees, and we respect our budgets very, very much. And having said that, we also track the cost of our actual AKS clusters. Okay, so where are we going? We are planning to expand into the department of event-based autoscaling. We consider using virtual notebooks for burstable workloads. We are going to be making considerable efforts to have monitoring and alerting based on Azure costs. So this is our FinOps. We're going to continue to work on a high availability. And having said that, we are also going to expand into the secondary region once we have achieved high availability in the scope of the first region. And we're also going to add more automation. And how are we doing? So we have 300 plus pods or 60 plus services in our cluster. There's a lot of activity going on. We are processing 80 million plus HTTP requests daily and 12 million plus messages daily. And the size of our storage after such a short time is just astonishing. So I'm actually quite afraid to estimate what it will be like at the end of this year. But I'm looking forward to it because more challenges are coming. Okay, so that's it. Thank you. And should you have any questions, I'm available now.
Dzięki Maciej za prezentację. Wiesz co, mamy jedno pytanie, ale tutaj Kamil pyta tak ogólnie, ale to przedłożymy też na Waszą infrastrukturę, czyli Allegro Pay. Allegro testuje swoją infrastrukturę, to znaczy celowo ubijając instancje na produkcji, tak jak to robi Netflix, za pomocą swojego House Monkey. Czy u Was w Allegro Pay macie coś takiego jak House Monkey?
Znaczy, w samym Allegro jest coś takiego, są eksperymenty, natomiast w Allegro Pay przymierzamy się do tego. Mamy już upatrzone z grubsza rozwiązanie, które jest zgodne z naszym stosem technologicznym i będzie się łatwo integrować, i to też nas nie minie.
Też Was nie minie. Czy mam jeszcze jakieś inne pytania, do których by Maciej miał Wam odpowiedzieć? Ja tu jeszcze tak uzupełnię, tak jak właśnie mówił Maciej, tak w Allegro jest to testowane, jest ten chaos wprowadzany. I nie tylko. Tak zwane są inne scenariusze, o których właśnie Maciej wspomniał. No chyba nie mamy pytań. O nie, jest. To teraz tak. Od Tomasza Kaźmierczaka, czy testowaliście inne rozwiązania typu Service Mesh?
Tak, w samym Allegro jest trochę inny Service Mesh niż u nas. My się zdecydowaliśmy na to rozwiązanie ze względu na jego prostotę, natomiast na pewno rozważany był przez pewien czas Console Connect, Istio było brane na tapetę, natomiast pod koniec dnia Linkerd wygrało.
Czyli jego prostota konfiguracji, tak?
Tak, szybkość wdrożenia, prostota konfiguracji i łatwość, z jaką nasze serwisy się z nim zintegrowały, plus fakt, że Linkerd ma ten mechanizm load balancingu oparty o średnią kroczącą, to EWMA, też w naszym przypadku był nie bez znaczenia, także tutaj wygrał. Patrzyliśmy także na performance i dane, do których się dobraliśmy, wskazywały na Linkerd jako na mocnego kandydata.